Rasmus Bro. I'm from University of Copenhagen, and today we have Raffaele Vitale from University of Lille in France, who is going to talk about how to compress freeway data in new fancy ways. So please, Raffaele, go ahead, and afterwards there will be time for questions, etc., or you can write them in the chat if you want.
Very good. So, good afternoon, everybody. Thanks a lot, Rasmus, for inviting me once again to speak during your Monday webinars. I'm always very happy and honored to be here with you, and especially to have the chance to share the latest advances of our research activities. So welcome to all of you. As Rasmus has already announced, my name is Raffaele Vitale, and I'm currently working as associate professor at the University of Lille in France, more specifically affiliated to the LASIR, a lab specialized in the development and application of spectroscopic and microscopic techniques for the characterization of complex life science systems. And today I would like to tell you about a novel algorithmic procedure we have recently devised in collaboration with our colleagues from Iran and the Netherlands in an attempt to reduce and compress data sets exhibiting three-way structures based on the principle of what we call essential information. However, before diving into the details of such a novel algorithmic procedure, allow me only for a few minutes to take a step back and show you where this concept of essential information initially stemmed from, and why, and especially in which scenarios it could be particularly useful for practitioners of chemometrics. To do so, though, we need to start by slightly reducing the degree of complexity and move just for a while from the realm of three-way arrays to the one of two-way data analysis, more in particular to the domain of bilinear curve resolution of spectroscopic data. Now, I'm almost sure that most of you already know that in spectroscopy, one often exploits analytical platforms providing signal profiles called spectra, which basically give insights into how light interacts with investigated samples. And I'm also sure that most of you also know that a spectrum constitutes a sort of fingerprint of the specimens under study, but that almost always results from linear combinations of individual signal contributions derived from, let's say, pure components underlying the explored systems, atoms of the same elements, compounds sharing a common molecular backbone, etc., as per one of the most popular laws we know in analytical chemistry, the Beer-Lambert's law. In this regard, it is worth noticing that it's actually these individual contributions, together with their respective combination or mixture coefficients encoding information about the abundance or the concentration of their corresponding components within the systems themselves, that permit to obtain an accurate idea of their intrinsic composition. Unfortunately, though, all these parameters are usually not known a priori and need to be somehow estimated from available observations. This defines what we commonly refer to as a blind source separation or a blind unmixing problem, whose resolution requires not only one, but a series of equations like this, characterized by a certain degree of variation in the aforementioned mixture coefficients. In other words, we cannot directly operate on individual spectral profiles, but we need to gather multiple of them for different spectral mixtures along the rows of a data matrix, say D, and carry out the bilinear factorization of this matrix as the product of two distinct submatrices, S and C, that contain the pure spectroscopic fingerprints of the components constituting the investigated samples, and their related abundance or concentration profiles over all such samples, plus, of course, some model residuals. Now, although there exists a plethora of diverse multivariate statistical strategies to successfully tackle this task, The very basic principle of this resolution or a mixing process can be easily conceived through the following example. Imagine that one has collected a series of spectral data on all possible mixture combinations of three different components. This means that the spectral profiles contained in this dataset can be underlain by a single pure component, a binary mixture of 2 out of 3 components in different proportions, or a ternary mixture of all the 3 components in different proportions. This is, of course, a simulated example, and for the sake of simplicity, here only 3 pure component spectra were accounted for, these ones highlighted in red. Now, the ternary mixture problem this dataset intrinsically encodes can be graphically visualized in a very simple, intuitive, and straightforward way. If I take this dataset, in fact, I subject it to principal component analysis, and I represent the resulting scores, the points associated to the aforementioned pure component spectra only initially fall within the scores point clouds without defining any easily recognizable direction in the PCA subspace. However, under specific normalization constraints, here, for example, I divided element-wise all component scores vectors by the first component one. This scores point cloud assumes what in chemistry is also known as a two-dimensional simplex geometry, very similar to the ones we are used to observe when mixture designs of experiments are concerned. In other words, each one of these represented points here is distributed within a triangle, whose vertices correspond to the so-called pure samples, those containing by definition only one of the 3 components under study, along whose sides are distributed the binary mixtures of the 2 components such sides actually connect, and whose internal area contains the ternary mixtures of all the 3 components considered. Now, given this particular representation, it goes without saying that for any linear unmixing approach, it would only be needed to somehow identify the vertices of this triangular geometry to readily solve the resolution problem at hand. And I think that everybody agrees with me on this particular aspect. However, contrarily to in unsupervised learning and statistics, the vertices of this triangular geometry constitute a specific case of what are also called archetypes. Generally speaking, archetypes correspond to the most linearly dissimilar observations of a multivariate dataset, support its multidimensional convex hull, and share an essential mathematical property. All the other objects of the dataset indeed can be expressed as convex linear combinations of archetypes measurement vectors. Now, based on what we have said up until now, it is pretty clear that in this specific case, finding archetypes would readily translate into spectrally unmixing the investigated data. However, contrary to this ideal situation in which pure selective information is available, in which pure samples were collected, and well, life may be slightly harsher. Why? Because most, if not all, spectroscopy experiments conducted on real-life systems leads to the generation of extremely redundant data. That is to say that all registered spectral profiles are normally underlain by linear combinations of the aforementioned pure signal contributions. And this would correspond to a situation like this, in which a partial or incomplete simplex geometry is observed across the subspace of the normalized PCA scores yielded by the data decomposition. Of course, here, archetype identification will not directly enable the resolution of this data set, for which proper multivariate spectral unmixing approaches would be required. Nevertheless, based on what we have said just before, that is to say that all recorded profiles can be somehow described as linear combinations of archetypes measurement vectors, it goes without saying that the archetypes of any mixture data set, once again corresponding to the points supporting its multidimensional convex hull, encode by themselves the purest information available. In other words, it is not necessary to assess entire data sets for the sake of linear resolution, as in principle their sole archetypes are already capable of driving the resolution towards the expected results. And this aspect can have a tremendous impact in such a domain, especially considering the fact that archetype selection can yield a dramatic reduction of the size of the data to be handled, while preventing any significant loss of meaningful or useful information for curve resolution or spectral unmixing. Now, let me stress once again this point here to avoid falling in a common trap that I'm sure Cyril knows very well, that is tormenting us since the very beginning of all this story. We are perfectly aware of the fact that archetype selection does not always guarantee the resolution of a spectral unmixing problem, since archetypes, as in this particular case, does not necessarily correspond to pure component spectra. What we only claim is that selecting archetype, or let's say essential spectra, and performing curve resolution solely on selected archetypes can yield an identical, in principle, data factorization as when full data sets are concerned. Now, let me give you an example of what is possible to gain in these terms by archetypes identification and selection prior to a mixing. Here you have a mid-infrared hyperspectral image of a pharmaceutical powder sample containing a mixture of three different compounds, citric acid, acetyl salicylic acid, and caffeine. And this is the representation of the reduced number of essential spectra, to be precise, 49, selected as shown before, together with their respective pixel locations. Now, when we talk about multivariate curve resolution of hyperspectral images, one should notice that we commonly assimilate them to regular collections of spectra, exactly like those I showed you before. Therefore, all that we detailed previously remains valid, with the only difference that the aforementioned abundance or concentration profiles become here spatial maps, highlighting how the individual components are distributed over the investigated samples. This being said, in order to compare the spectral unmixing carried out only on the ensemble of selected essential spectra and on the entire dataset under study, we applied to both of them one of the workhorse chemometric algorithms conceived with this purpose, multivariate curve resolution alternating least squares, also known as MCR-ALS. As one can easily see, the pure spectroscopic fingerprints extracted in both cases are in perfect agreement and contain all the absorption bands expected for the three different chemical constituents considered. Also, the so-called component distribution maps yielded by the two distinct decompositions performed are basically identical. Just mind that when running MCR-ALS on the subset of essential spectra, these maps are not readily output by the algorithm, but need to be somehow reconstructed through a non-negative least squares projection of the entire dataset onto the subspace spanned by the three resolved spectral profiles. Summarizing, same resolution obtained here, but of course analyzing only around 2 or 3%, as far as I remember, of the analyzed spectra, and of course in around 3 times less computational time. Now, the amazing thing behind this concept of essential information extraction regards the fact that such an approach is not limited to only one of the modes of the data under study, but can in principle be extended, for example, to both rows and columns of a data matrix. This way, one could think of achieving even higher data compression rates while reducing not only the number of spectra, but also the number of spectral variables to be processed. For a joint selection of essential spectra and essential spectral variables, adapting the methodological procedure I showed you before is basically straightforward. It is only required to estimate the convex source of the normalized PCA scores point clouds of the original data matrix and of its transpose. And if I consider the same example I showed you before, by such a joint selection, I can accelerate even further the MCR-ALS analysis of my hyperspectral image as shown here, obtaining once again virtually indistinguishable spectral unmixing outcomes. And now I believe I really don't need to say much about how to modify this selection strategy for handling three-way data sets. Well, actually, I don't agree with myself in this case because something particularly important must be said. We need, in fact, to replace the preliminary bilinear PCA decomposition step with a trilinear one for the dimensionality reduction of similar arrays. And luckily, in this case, Mr. Tucker comes to our aid. In the 60s, indeed, he proposed a method called higher order singular value decomposition, or HOSVD, that can actually be regarded as a sort of multi-way or n-way extension of principal component analysis. Just for the details, HOSVD returns a Tucker tree model encompassing all possible extractable components and characterized by fully orthogonal component profiles along all the data modes under study. And operationally speaking, such a model is retrieved by performing standard singular value decomposition on the two-way matrices resulting from the row-wise, the column-wise, and the tube-wise unfolding of a generic three-way array. So, once performed HOSVD, it is only needed to somehow take the scores yielded for all the three data modes considered, truncate them and normalize as shown you before, and finally estimate the convex source of the three resulting normalized HOSVD scores point cloud to be capable of identifying and extracting essential rows, essential columns, and essential tubes of a three-way array. And let's now consider whether the advantages deriving from the selection of essential information in bilinear spectral unmixing remain valid even when three-way data sets, and especially trilinear curve resolution approaches, namely parallel factor analysis alternating least squares or parafac ALS, are concerned. The first practical example I'm going to show you regards a set of time-resolved fluorescence spectral data we collected in our lab on 9 mixtures of 3 fluorescent dyes, Alexa 647, Alexa 655, and Alexa 665. For every mixture, 8 distinct fluorescence decays were recorded at 8 different emission wavelengths, which resulted in a three-way dataset of dimension 9 samples times 2,500 time points times 8 emission wavelength channels. Here you have a very schematic representation of this data set in which I displayed for every mixture sample an individual fluorescence decay integrated across all the spectral channels and an individual spectral profiles integrated across all the decay time points. This data set, of course, is assumed to exhibit trilinearity among the aforementioned measurement modes, since also these fluorescence decays follow multi-exponential function that, as we said before for the spectral profiles, are the combination of mono-exponential contributions, each one related to a given fluorophore under study. Here, the approach I showed you in my previous slide yielded, enable the identification and selection of 6 essential rows, 24 essential columns, and only 5 essential tubes that, together with the original full data set, were submitted to ParaFac-ALS for their trilinear factorization. As one can easily see here, all the 3 component mode loadings profiles retrieved from the subset of essential data only are basically virtually indistinguishable with respect to the ones resulting from full-size measurements. However, the computational time required to estimate them was found to be about 800 times lower than the one obtained when such full-size measurements were analyzed. If one has also a closer look, for example, at the essential rows selected, please see the dashed line in this figure, it is evident how 4 out of 6 relate to chemical mixtures constituted by only 2 of the 3 fluorophores considered, and for which the ParaFac-ALS loading profile of the missing component assumes values basically approximately to 0. Approximately equal to 0, sorry. This clearly evidences how the essential information-based selection procedure is actually capable of reducing the redundancy of the information encoded in the investigated data prior to their final decomposition. Emission wavelengths characterized also by a strong overlap among the 3 different ParaFac-ALS loadings profiles were satisfactorily identified as non-essential and therefore excluded from the compression operations. The second example concerns instead a 246 times 238 sequential illumination fluorescence image of bone tissue cells affected by osteosarcoma and stained with a combination of 2 different fluorophores, DBAC4-3 and Concavalin A Alexa 488. The pixels of such an image are underlain by 6 different fluorescence decay that here, for the sake of simplicity, I represented all together in the same plot. Recovered over 45 consecutive time instants across a series of 6 photo-bleaching recovery cycles. During these cycles, the laser power was modulated differently in an attempt to emphasize the distinctive dynamic behavior of the various fluorescent species bound to the individual compartments of the system under study. Also here, these decays follow multi-exponential function as the ones I showed you previously, that are the combination of mono-exponential contributions, each one related to a fluorophore located in a particular chemical environment. Clearly, before parafac ALS processing, this image was preliminary unfolded pixel-wise, which resulted in a three-dimensional data structure of size 58,548 pixels times 6 photo-bleaching photo-recovery cycles and 45 time points, assumed once again to exhibit trilinearity among the pixel, the cycle, and the time mode. As one can easily see, also in this case, the essential information base reduction procedure yielded a significant compression of the data at end, which permitted to attain in a substantially lower amount of time, namely approximately 30 times faster, a trilinear factor model that is basically indistinguishable from the one resulting from the decomposition of the original measurements collected. Please notice that in this case, the number of factor profiles was set to 3 based on preliminary knowledge available on the number of components expected to be observed in the capture scene. Also in this case, the essential rows, the essential columns, and the essential tubes selected correspond to rows, columns, and tubes in correspondence of which distinctive cellular compartments can be found. The overlap among the parafac ALS loadings profile is minimal, or their trend is not particularly correlated, which demonstrates once again that the proposed approach is capable of significantly reduce the redundancy of the information encoded in the investigated data. And here I want to conclude, summarizing the fact that we proposed in this work an approach for the reduction of three-way data arrays based on the principle of higher order singular value decomposition that basically extends previous works to the domain of three-way data compression. This approach is capable of retaining the most meaningful information required for a sensible trilinear factorization of such three-way arrays, which is the main difference between this technique and other already proposed strategies, often relying on the principle of random samplings. The parafac ALS decomposition of the reduced data obtained this way yield almost in principle virtually indistinguishable loadings profile with respect of the situations in which full data sets are analyzed, and can take up to 800 can be up to 800 times faster than when parafac ALS is run on full size data. And of course, parafac ALS model quality and adequacy is preserved even after this compression procedure is carried out. Rasmus, I still a couple of seconds of the presentation just to ask a question to you and to all the invited people that are here today. At the moment, the higher order singular value decomposition based approach we proposed basically accommodates almost, I would say, perfectly the structure of a parafac ALS model, because basically we extracted the same number of factors for all the data modes under study. And my question was the following: would it make sense to somehow modulate the compression, trying to extract a different number of factors for individual factors to somehow accommodate better the inherent structure of alternative trilinear factorization models, like, for instance, Tucker variance, paralleled, or similar? And I take some time as well for a bit of advertisement, Rasmus, if I can, just to advertise two events that I am directly involved in. The organization of the next Colloquium Chemiometricum Mediterraneum that this year is organized in France by us, and that will take place on the island of Porquerolles in the south of France in September 2025, as well as closer, I would say, event that will take place in Coimbra in Portugal in May, That's an MBIS spring meeting. MBIS is the European Network of Industrial and Business Statistics. And well, this event is mainly devoted to young scientists willing to share with us experience this year on quality by design and process analytical technology, and more specifically on the application of purely data-driven, say, statistical or AI approaches and gray approaches, let's say, mixing first principle modeling with totally data-driven modeling. And with this, I thank you all for the attention.
Thank you so much, Rafael. That was beautiful. I have some questions and comments, but before I would like to ask people if there are any questions, comments, etc. Then you can write it in the chat, or if your microphone is good, you can just ask the question.
Hi, Rafael. This is Paul.
Yeah.
I was just curious, the comparison of the times, the computation times, does that also account for the time you need to find the essential information?
Yes.
Yes.
Okay. So this is basically a comment that we received after the first round of review of our paper. Basically, the computational time that I indicated every time I compare the Parafac ALS run on the full data and the Parafac ALS I run on the reduced data takes into account the selection, so the identification of the essential rows, variables, and columns, the decomposition of the reduced data, as well as the least squares projection of the full data to reconstruct the full size loadings profiles, let's say.
Okay, well, that's really impressive then. And yeah, thanks for the talk. I mean, it's really interesting.
Thanks a lot, Paul. Thanks.
And we have Cyril just put the paper in the chat, so you can check that there. And let's see, did we have a question down here? Yes, there's a question. I'm working on GCMS. I would like to know how can this technique be applied to this type of data with the issues of retention time shifts?
Yes, that's true in the sense that well, this is I would say a more classical problem than only related to the compression, because in a certain sense one should guarantee the trilinearity or the multilinearity of the data sets for a further decomposition. I don't have a direct solution for that, unless, because we were discussing with Rasmus before this meeting for a couple of times. And unless this proposal, let's say, of trying to extract a different number of components per mode might help in this case, because in my opinion, at least as far as the algorithm is coded and the approach is proposed, we are not really able to handle automatically pitch shifts or band shifts, because this anyway it constitutes a breakage of the linearity, so goes a bit beyond the rationale of the algorithm itself, and it enters more the most fundamental question of multilinearity properties, let's say. I'm not sure whether this kind of approach, once again, let's say selecting different number of factors per mode, might help in this kind of situation.
Yeah, sorry, Osman, I will just add, I agree with you, and I think then, for example, if you do Parafac 2 to handle the shifts, then you can just handle that there's an additional complexity. The rank in that mode is higher, so you extract more.
Exactly. And in fact, this goes along this kind of question, in the sense, can we modulate to somehow also accommodate structure like Parafac 2 models? Anyway, I was now thinking, and probably an idea popped up in my mind. If along the retention time mode you have shifts, why not unfolding on that mode and try to apply essential information selection on the resulting two-way matrix. That's something that can always be done as a let's say ready to use solution that one can try. Let's say.
Yeah, and that goes with what Cyril said.
Yeah.
That it's variable selection he wrote in the chat.
Yes. Yeah.
It's not the subsequent aspect
Yeah.
you're covering.
Yeah.
It's how to just represent your data.
Yes. Yeah.
Okay, sorry. I think Osman, now is your time. I kept you away.
Thanks, Cyril. Thanks, Rasmus, and thanks, Raphael, for the presentation. I can see that the models that you are playing with are rather simple in my mind with the complex samples that we are looking at. How does it, and we have just experienced that using like a general least squares procedure or like a general trilinear decomposition does not give the global minima ever. Have you played? Do you have any?
So to be honest, I have not played with really complex samples, let's say, in the three-way domain, let's say. But we have analyzed systems characterized by 8-9 components, namely pharmaceutical system, characterized by 8-9 components in let's say by two-way approaches, so standard MCR ALS, and we have rather surprising results also in that case. The only thing that you will pay the, let's say, the price of is the number of essential spectra or essential spectral variables that you will select, because you will need somehow to increase the number of components along which you perform the selection to catch all the sources of variabilities underlying your system. So this will mean that you can always increase the number of components. Of course, you will pay the price of having to analyze a larger number of samples, but sometimes we had surprising results also in this particular scenario when dealing with minor components. That is to say, among the 7, 8, 9 components, you have sometimes one component that only appears under few pixels. I agree with you. In that case, least squares based approaches may not handle this kind of minor components because somehow they will adapt the models to the major components, using this kind of trick of reducing the size of the data. It seems, at least to many, in many cases, we handled that you can approach easily this global minima, at least in two-way data analysis. I'm not sure if in three-way that's the case, because I've never, let's say, we have never collected data on systems more complex, that would say 4 or 5 components. Actually, when dealing with this kind of fluorescence techniques, is already particularly complicated to get images or data underlying by 3 or 4 fluorophores, then that thinking of increasing the number of fluorophores or chemical species spectroscopically active for us is a bit complicated, let's say.
Thanks.
Thanks, Osmond.
Okay, can I ask you if I expect if your initial PCA or whatever is too small, I mean too few components, that's going to be an issue.
Yes, that's totally correct. It's more an underestimation of the complexity that is dangerous than an overestimation.
Yeah.
If your rank, let's say, is underestimated when you lose a component, and then your selection, your reduction, let's say, will not take into account the influence that that component had in the original data. Of course, you can always have, I always say that this problem is important, but it's not that important, because you can always stay a little bit more conservative and say, okay, I go on with the number of components, I overestimate my rank, the price to pay is simply I will not reduce the data as much as in the ideal case, but in that case you will be sure that all components contain contain information related to all your chemical components of your system. this is something we commonly play with, and this is actually the main difference you have with these random sampling approaches. Random sampling, yes, of course, if your component is distributed randomly or homogeneously over, for example, an hyperspectral image, everything is fine. But if you have minor components, then random sampling might not be the ideal solution, let's say.
Yeah. But how much I would kind of guess that when you increase the rank, it kind of explodes a little bit, the number, or what? I mean, the number of members of the convex hull.
It increases, it does not explode.
dramatically.
I mean, you cannot select more than your original data set. So if you can handle in a certain sense your original data set, you might be able to handle also, let's say.
But it doesn't increase.
Well, that's something I've never tested. If you mean if the trend of increase is exponential or linear, that I don't know, to be honest.
No, okay. I would just expect it to be more than linear, but
okay.
I don't know. Maybe Paul has an input. Paul?
No, I don't really have an input for that. I had another question, well, maybe related to this, because have you practically made any experience with sequentially modeling? Like if you start with 3 principal components and then you see, the information that I received is nice, but then you continue modeling the data set with the, let's say, 4 to 6 principal components that you have not looked into, because I think actually you can kind of nicely unpeel the data maybe in that way, because it's all orthogonal, right?
So what regarding this, rather than in our case, it's much more interesting. Rather than playing with the components, of course, this is also nice. You can also implement what is called the convex peeling within the selection. That is to say, instead of selecting only the samples belonging to the first convex hull, what you can do is you select the first convex hull, you remove, then you continue selecting the convex hull. So in this case, you will reach, in a certain sense, gradually the most internal area of the simplex. So you will anyway select let's say the purest samples, columns or tubes available. Just you would be a bit more robust because, of course, in real case study, you might have outliers, you might have noise that somehow generate observations that cannot be described as linear combinations of pure component spectra. So you will definitely select them. But if you play with the sequential convex peeling, you can robustify the whole procedure in that sense. But this is, let's say, something that we did previously in a bilinear curve resolution. We weighted, let's say, the resolution based on this kind of approach of convex peeling, and this somehow robustifies the estimates. Robustifies the estimates means that your estimates become less uncertain, because, of course, if you reduce too much the data, well, noise will take somehow a big influence with respect to the structure, and of course it can perturbate the uncertainty of your estimates. But if you play with this kind of convex peeling, you can robustify the whole procedure in this sense. This is the only sequential modeling strategy that we explored so far. Of course, sometimes when you don't have a satisfying resolution with 2, 3, 4 components, you can always try to increase the number of components up until somehow the resolution you obtain makes sense to you or can be interpreted by an expert, etc. This is, of course, something that we often do when dealing with new data, let's say, about which we don't know much. That's my experience on this point. I don't know if I answered your question, Paul, but
yes, I just thought a practical solution could be you calculate it on 3 components, then you can subtract the 3 components, the information of the 3 first principal components from your data, and then just repeat, go on, and I mean your strategy of this unpeeling is really.
You mean about the number of when the number of components increases? That's what you mean?
Yeah.
Okay. So I have a sensation about that because this is based on some test I've preliminary done. When you select with 3 components and you deflate afterwards to select once again on the residual 3 components, I'm not sure that selecting over 6 components compared to selecting first on the first 3 and then on the second 3 is the same. And you know why? Because geometrically, a polyed, I don't know how to say, a polytope in 6 dimensions cannot be necessarily described as a combination of 2 polytopes in 3 dimensions. Even if the dimensions are orthogonal. We have experienced that in the sense that if you select, we tried that, if you select in a subspace of 6 principal components and you select on all possible combinations of 2 components among the 6, the selection is not the same.
Okay, yeah, that answered my question.
Okay.
I was too
Sorry,
naive.
I probably
Thanks so much.
your question. Sorry, yeah, okay.
No.